To test intelligence, whether human or artificial, researchers often start with something simple. The 1970s arcade game Pong is a perfect baseline. It's easy to understand. Move a paddle, stop a ball. Now researchers have taught a completely new kind of player: living human brain cells placed directly on a silicon chip. This experiment targets a specific share of the $500 billion global AI infrastructure market. Researchers are leveraging these neural clusters to prove that biological hardware can handle complex digital tasks. The global race for artificial intelligence requires immense computational power. To keep advancing, companies are realizing they need to move past standard code and reinvent the physical hardware that processes it. Intense market competition and geopolitical tensions are driving massive demand for faster, more efficient AI models. You can see this pressure embodied by NVIDIA CEO Jensen Huang, currently sitting at the center of a historic hardware boom. For over 50 years, the industry relied on an observation made by Intel co-founder Gordon Moore. Moore's law predicted that the number of transistors on a microchip would double every 2 years. But the industry is hitting a physical wall. To keep doubling, engineers are depositing layers of material that are now just 1 atom thick. You physically cannot go any smaller. Because we can't make chips smaller, we are just building more of them, creating a compounding energy crisis. By 2034, data centers are expected to consume roughly 1,580 terawatt-hours yearly. To put that scale into perspective, that is roughly the total energy usage of the entire country of India. A modern supercomputer requires up to 40 megawatts of power to function, along with massive, complex cooling systems just to keep the silicon from melting down. Compare that immense draw to the biological alternative. While a supercomputer pulls 40 million watts, the human brain runs on just 20 watts. With that energy, the equivalent of a couple of LED light bulbs, it efficiently operates 86 billion neurons and 100 trillion connections. Tech giants are staring at a power grid that literally cannot support their future data centers. The only viable path to surviving their own energy appetite is to leave pure silicon behind and steal the incredibly efficient blueprints of biological evolution. To harness that biological efficiency, deep tech startups like Cortical Labs in Australia and Final Spark in Switzerland are manufacturing the first generation of biocomputing hardware. They are taking living cells and directly integrating them with synthetic systems. Cortical Labs built a system called DishBrain. They cultivated roughly 800,000 living neurons directly on top of a synthetic surface. This schematic illustrates the translation mechanism required for the hardware and wetware to communicate. The underlying chip is divided into 3 distinct zones: a larger sensory section at the top and 2 smaller motor sections below it, one for moving the digital paddle up and one for moving it down. Because neurons naturally communicate using electrical impulses, researchers can feed the digital environment of a video game directly into the cells. Information about where the Pong ball is located gets converted into electrical signals that flow into that sensory zone, allowing the biological tissue to physically feel the game. This architecture creates a literal bridge. By placing living tissue onto a physical routing map, synthetic hardware and biological cells communicate directly, erasing the traditional boundary between man and machine. Connecting the cells to the game is an engineering challenge, but getting them to actually play it is a programming problem. A cluster of neurons sitting in a dish has no inherent genetic motivation to care about a digital paddle. To make them care, researchers rely on a theory called the free energy principle. This principle suggests that all biological entities, no matter how small, are constantly trying to understand their environment, to minimize surprise and avoid chaos. This logic diagram demonstrates how researchers weaponize that survival instinct. When the brain cells miss the digital ball, the system triggers a miss state, stimulating the neurons with a messy, scattered, and jagged burst of unpredictable electricity. The cells naturally avoid this chaos. On the other hand, when the cells successfully hit the ball, they receive a hit state. The chaotic signals are replaced with a clean, perfectly ordered sine wave. It's a soothing, predictable electrical stimulus. Within minutes of applying these distinct stimuli, the cells start hitting the ball more consistently. To avoid the chaotic shocks, The biological neurons literally restructure their physical connections to master the game's environment. A traditional silicon chip is rigid. It is forced to execute sequential logic exactly as a human coded it. Biological wetware organically rewrites its own hardware to survive its environment. While the tech industry wants to use these organic models to power massive data centers, biomedical researchers see a completely different application. They are using living processors to study neurodegenerative diseases, allowing them to bypass the slow and often inaccurate process of animal testing. In the lab, a researcher can train a tiny spherical cluster of neurons, known as a brain organoid, to learn specific tasks. They can then introduce a disease like Alzheimer's into that tissue and precisely measure how quickly the organoid forgets those tasks compared to a healthy control sample. This chart visualizes a massive upcoming healthcare crisis. Driven by an aging population, global brain disorders are projected to increase by 22% by 2050. Over a third of the entire human population will eventually suffer from conditions like Parkinson's or dementia. The same hardware being designed for AI infrastructure gives pharmaceutical companies a platform to observe human cognitive decline directly. This provides a human-specific model for testing therapies that animal studies often fail to predict. It constantly pumps fluid around the tissue to feed it, cleans out the biological waste, and rigidly maintains the internal temperature at exactly 37 degrees Celsius. That temperature control highlights a major engineering clash. Traditional computer chips draw hundreds of watts of power and throw off intense heat. If you place fragile biological material right next to a traditional processor, you risk literally cooking the living computer. Beyond the plumbing lies an escalating ethical dilemma. As these brain organoids scale up to handle more complex computing tasks, researchers must question if these dense clusters of human tissue can feel pain, and whether it is ethical to simply unplug them. The semiconductor industry required 50 years of development to achieve its current global scale. Biocomputing is just beginning that journey, leading toward a future where our most powerful machines may no longer be built, but grown.